start the webinar right now. Okay, so people can start to log on. So Zhehong, maybe you can quit sharing your screen right now.
Let's see.
For a moment.
Yeah, it just flips for the beginning. Oh, you want to close it, or you want to keep the my screen on?
You want to you want to quit sharing your screen for a moment?
Sure.
And then we just need to make an announcement or two, and then
Okay, I may have to stop my videos.
yeah. We generally start about 5 minutes after the hour. That's when MIT classes start, so we give people time to arrive. Huh?
Yeah, I can see the number of participants going up.
So Art Palmer says Columbia starts 10 minutes after the hour. Thank you, Art.
Always 5 minutes behind MIT. Actually, it's only the main campus that starts 10 minutes after the hour. The medical school starts on the hour. So,
well, that means you have classes that are only 40 minutes long.
Right. The typical class runs like my class with Ann this afternoon is 4:10 to 5:25.
Well, yeah. And Alex Pines says Berkeley is 10 minutes after the hour as well.
Looks like MIT is an outlier.
Hello, Alex.
You wanted to, you requested me to unmute because usually you're the first one to mute me.
Well, I can do that if you.
I know you can do that. I can do it myself too. Bob, you can hear me, but you can't see. Can you see me as well?
We can see your logo there, or whatever it is. Yeah.
Oh.
Yep.
Oh, now we can see you.
That's my real face.
Right.
Now I can see people. Okay, there's Glaubitz. Okay, I see. Yeah, hi, Zhehong. Nice to see you again. It's been a while. Been a while since I saw you, Bob. I've been away for quite a while. I'm finally coming back to. I guess I'm coming back to my full 50% capacity. The group has said, Alex, could you please stop at 20? So I'm up at 50, and that's about where I think I'll asymptotically rest. How have you been?
I'm fine. I hope you're okay now. No, that's good.
It's been a long haul for several months. It's been a tough gig. I don't talk about it right now, but just say
yeah. Okay, well, it's good. Yeah.
The way I'd phrase it now is that I can finally make out the dark in the middle of the tunnel.
Good. Good. Progress. Progress. Yeah.
So who else do we have? I see 5 people here. All right, but I'm gonna unmute. Let me see. I'm going to mute because it should start momentarily. I want to hear what Gan has to say. And
All right, so why don't we, well, actually, we have another
We
minute.
have 2 minutes, yeah.
Yeah.
that's enough time to devise a couple of new pulse sequences, Gan. 2
Right.
minutes. I mean, Griffin's pulse sequences take 1 minute each, so that's 2 pulse sequences.
All right.
MIT is more about quantity than quality, I'm afraid. Yeah. Okay, I'm out.
Hey, Kong, do you want to say anything before we get started?
Yeah, I can say something simple, but perhaps not long. Yeah.
Okay.
All
All right, why don't you go on? It's 11:05 now. Okay.
Yeah, okay. I mean, like, even though like on my computer it says like 04, but it's okay. But first of all, like, thank you for joining like us again. Like, it's a fresh start of the year 2021. We wanted to start like the first session 2 weeks ago, but unfortunately, like, we cannot find a speaker, so apologize for that. But right now we have the schedule until we have scheduled speakers until like end of March, end of April, something like that. So so it's nice to see you again, and then like I hope like this series will perhaps like go on for maybe until summer, like, because like at some point we need to stop again. But apart from sharing science, it's also nice to see everyone like chatting here and saying hi and keeping the community connected and greet each other. So a bit more on the bookkeeping side. If this is your first time like logging on to this ZOOMinar, I would encourage you to sign up to our mailing list, and also like if you are interested in listening to the past talks, the past seminars, we have like recorded like a lot of them. If the speakers have given us the permissions, you can find all of them on our group, on the Griffin group website. And also like feel free to use the Q&A button that you can see at the bottom of the Zoom interface. You can type your questions, and otherwise, if your question is too long, or if you feel like it's easier for you to ask the question verbally, but feel free to do so. You can just raise your hand, and I will allow you to speak, and you can ask your questions. I will copy and paste all the links and whatever you need on the mailing list information in the chat room. So I think that's it from my side. So I will now pass the session to Bob so that he can introduce our two very interesting speakers today.
Okay, so today we have two excellent talks, excellent presentations from two really very distinguished scientists in our field. Zhehong Gan, who's from the National Magnet Lab in Florida, and he's going to tell us about long pulses and quadrupolar nuclei. And Clemens Glaubitz from the biochemistry department at Frankfurt University in Germany, and he's going to be telling us about DNP experiments on nascent chains. So with that very brief introduction, Zhehong, why don't you take the floor, the virtual floor, and tell us about your recent work with long pulses for quadrupolar nuclei.
All right, thank you, Bob and Con, for the kind invitations and also for organizing this wonderful series. And also it's an honor to kick off this series, to be the first speaker to kick off this series for the new year. So I will talk about two parts. The first part I think is a high field, which we do at the Mag Lab, and also talk about the use of long pulse for solid state NMR of quadrupole nuclei. Let me see. Why here beep? Okay. So here's the 36 Tesla, we call the series connected hybrid magnet at the Mag Lab. We have been running this for more than 2 years now. It's a powered magnet, so they need the infrastructure for its operations. It's a hybrid magnet together, it's a powered inside a superconducting outside magnet, which is sitting behind the ion shield right here. And everybody recognize the NMR console, and the excess of magnet from the top, which you can see probe at here in the picture. And in terms of bore size, after active shim and coil for field regulations, it leaves us a 40 millimeter, which is standard narrow bore size of an NMR magnet. So before I start, it's a big magnet, big project, involve contribution from many people from the construction of the magnet. I won't read out the name, but it just show the list of name, the people here, and also include the people for the operation, the RF group for the NMR instrument setup, and a group of people for running the NMR spectroscopy, and a list of the collaborator or users of this instrument, which I will show in the next. Oops. So a bit more about this magnet. It's a powder magnet. So the resistive insert take up to 12 megawatts. It requires up to 12 megawatts for at the peak field. And the superconducting magnet stores lots of energies with big coils. And the resistive part requires cooling water to take the heat out. And the superconducting part requires continuous flows of supercritical liquid heliums to keep the wire in a superconducting state. So because the powder magnet, we ramped up before we start experiment, and it takes about 30 minutes to ramp it up. And a typical day is we have about 8 hours running time, and we run 4 days a week, and approximately between 20 and 30 weeks per year. So that gives you a rough idea about the amount of time we have been using this magnet. And I would like to say that because it's powered and it's also has a bigger superconducting coil, it can quench. When that happens, all the energy stored need to be dumped into external resistors, and that will cause flash and sound. It does sound quite scary, but this magnet is designed for this kind of events, and it can be back in operation in about an hour or so. So now about, we use a lot for quadrupole nuclear for obvious reason, because the high field will benefit in terms of spectral resolution and sensitivity, because reduction of the quadrupole broadening by the high field. So here, and among all the nuclear, the one we do the most is oxygens. So here the example of oxygen of alpha formate MOF, magnesium MOF from Zhehong group at University of Western Ontario in Canada, by comparing the 1.5 gigahertz with the otherwise 900 data for both as made sample and also activate MOF sample after the preparations. So you can see the high field gives slightly more features, but still not much resolutions. And the signal noise is roughly comparable, but the acquisition time for the 1.5 gigahertz is about an hour or so, whereas the 900 data takes about overnight. So the enhanced sensitivity allows us to use two-dimensional experiment introduced by Richard Friedman, the 3QMS, to resolve, hopefully resolve more sites. And with the probe built out by engineer Peter Gorgoff, were capable to develop very strong B1 field, where we're able to obtain 2D MQMAS spectrums in about 4 hours or so. So here is the spectrum for the maiden sample and also for activity samples. And with the help, we can see that much more resolution in the 1D spectrum. And with the help of DFT calculations, and they are able to identify all 12 sites. I mean, some are partially overlapped, but they are able to identify all the 12 sites, and also monitor the change of the quadrupole coupling parameters and the chemical shift due to the interactions, between a host and gas interactions between the solvent and the MOF. Biological sample is also of interest for, also 17 NMR is also of interest for biosolids. So here the example of 017 NMR of oriented gramicidin A, which is ion channel. Tim Cross has been studied for many years now. And in the past, for from all carbon, nitrogen, and even oxygen NMR up to 900 megahertz, we see a single peak for every site of the molecule. Chromosidin A channel is a dimer, which indicates the two molecules are symmetric. To our surprise, when we acquired the O17 spectra at 1.5 gigahertz, we see the splitting of the O17 signal, which means there's some break of symmetry here, making the two molecules inequivalent. So here's the model that Tim and his collaborator come up with the file of water wire inside the water channel. The polarity of the water wire breaks the symmetry to split the oxygen resonance through the hydrogen interaction with the carbonyl oxygens. And we are able to see the result indicates the lifetime of this water wire is slow on the time scale, in the inverse of the splitting on the peak, which is much slower than what the MD simulations had anticipated. So this is, a surprise to them based on the NMR result. So let's see. And we also do nuclei other than oxygen. And one of the another popular one is zinc, which is very challenging because the low gamma and the low natural abundance, and the quadrupole moment is very big. So here's an example that from Sabyasachi Sen at the UC Davis, and also Professor Yue's group in Denmark. They are using zinc NMR to investigate disorder induced in the ZIF glass, which is another special kind of a MOF by melting the quench. So the spectrum on the top shows the deconvolution of the two crystal equivalent site in the crystal sample. And the bottom shows the change of the zinc spectrum from the crystal to the glass after melting the quench. And we can clearly see the increase of quadrupolar coupling due to the loss of symmetry of the tetrahedral zinc side. And the spectral line shape shows typical disorders for quadrupolar spectrums due to the distribution of the quadrupolar parameters. And we also do nuclear, more sensitive nuclear, abundant nuclear like boron. These are the very sensitive ones, but still it can help a lot for in terms of resolutions, and in some cases at running challenge experiment with low efficiency. And here's an example from Rick Dorn, from Aaron Rossini's group at Ames, looking at use boron NMR to study boron nitride, porous boron nitride. And the 1D spectrum here clearly shows improved resolutions by going from 400, 600 to 830 to 1.5 gigahertz. And the line narrowing certainly makes some kind of a weak, the weak signal hidden beneath the broad signal more obvious when you go to high field. And the increased sensitivity also allowed them to acquire the boron double quantum correlation spectrum very quickly to identify all the connections among the various boron sites, particularly among the site of the defect where all the activity occurred. Last, I will show just some kind of more of curiosity rather than taking advantage of the full field is overtone magic angle sample spinning spectrums. And overtone is a direct observation of the forbidden double quantum transitions, but the quadrupolar coupling make it slightly observable. But it itself is modulated by the spinings. As a result, both the excitation and the detection are shifted by the spinning at twice the spinning frequencies. And oddly enough, that the direction of the shift depends on the spinning direction relative to the field. So showing here, because of powder magnet, we can quickly reverse the field direction from minus 36 Tesla pointing up to 30 Tesla pointing down, and to verify this observation. So this is a very rare case. Actually, the spinning direction or the field direction matters to NMR. So now I'm going to switch the topic from the long pulse, and I will particularly mention this has been a long collaboration with my colleague, Dr. Ivan Han. We have been working on for many years on developing NMR methods. Before talking the long pulse, I talk about the issue of bandwidth. Because when we work with quadrupole nuclei, for example, like N14 satellite transitions, we are talking about the bandwidth of few megahertz. And we know that for a pulse, that the bandwidth, the sync function, for the excitation profile for a rectangular pulse is proportional to inverse of the pulse length. So we need to use shortened hard pulse, but 7 megahertz is probably a little bit too much, given the limitation of the I field and the probe tuning bandwidth. So we need to seek alternative. The alternative is going long, by making the pulse longer, at least 1 rotor period. The reason of doing that is because all these powder pattern is anisotropic, so they are modulated by the sample spinings during 1 rotor period. And as long as you place the IF within the powder pattern, there will be level crossings between the peak frequency and the IF frequency. And then that pulse can become effective. This is the same in a way very similar to the frequency sweep pulse like Wurst of chirp. But in that case, we sweep the frequency for a fixed peak. And everything can be well planned and designed. But in the case of a magic angle sample spinning, it can be a little more complicated because the where and when the level crossing occurs varies with the powder samples. And also for quadrupole nuclears, it's not a simple 2-level systems. It involves many more transitions and more energy levels. So in the next, I will talk about how to treat this kind of the IF spin dynamics in theory and apply it to the case of N14 HMQC. And more recently, we extend this kind of long pulse for STMAS and MQMAS experiment. To treat we use average Hamiltonian theory, but you need to go to the so-called quadrupole jolting frame. Jolting frame actually is a term that they introduced many years ago by Calvati, Bodenhausen, and Ernst. Basically, is a rotating frame of the modulating offset. By doing so, you eliminate the offset term, but introduce modulation to the IF field. And it break into the modulation, the Fourier component, which actually is the spinning sideband of that modulating powder patterns of frequency. So we can apply the average Hamiltonian theory. So the result actually is very simple. Normally without if for on-resonant IF, the IF Hamiltonian is omega-1 times IX. But if you have a very large, broad oscillating powder pattern, then the effective IF Hamiltonian will be scaled by the spinning sideband intensity. And interesting, it will be phase shifted by the phase of the spinning sidebands. And I should emphasize that the spinning sideband we'll talk about is individual crystallite, which can vary a lot among all the different crystallite, which is the powder averaged one, then they all becomes all phased. So in terms of the scaling factor, you can estimate from the normalization and the number of spinning sidebands, which is only the width of the powder pattern divided by spinning frequency. So we can estimate as a square root of omega r or omega q. But this phase distribution we must deal with because it can cause signal cancellations. A very simple example, if you apply a long pulse to N14, you end up with nothing because all the phase, even though all the individual crystallite get excited, but they all have different phases. So you get no net signals. But the situation would be very different if you use a pair of a pulse. For example, in the HMQC experiment, in the indirect dimension. In that case, because both pulses have the same phase shift, it does not affect the encoding of the N14 frequency. In the picture of the coherence transfer pathway, as long as the coherence order, the change of coherence order is opposite between the two poles, then the phase distribution cancels each other, result in no signal cancellations. So here we use long pulse, a rotor-period long pulse for the DHMQC experiment for N14. And also we even make the shift the recoupling to the N14 channel, make the pulse longer, just CW, long CW pulse. We call the trapdoor HMQC, which the trapdoor recoupling has been known for many years now. And we can also, the case also including in the double CP experiment from proton to nitrogen, then back to proton for detections for the heterocorrelations. That sequence was introduced by Bolton-Harding group several years ago. And because this kind of a long pulse has avoid the phase cancellation and also solve the offset problem, we can get very high efficiency. In this case, between 15 to 20% as compared to the, for the filtered, the first T1 increment as compared to the just a regular spin echo, proton spin echoes. And here the spectra, the DHMQC, because recoupling apply on the observed nuclear, so we have some T1 noise issue because the timing of from the spinning speed fluctuations. The DHMQC is very robust, and especially in terms of setup, and requires no calibrations and very little T1 noise. The double CP has an advantage that the proton T2 does not contribute to N14, so that's why it shows narrow line widths. But the spin diffusion among the protons can cause related peaks during the relatively long spin lock period. So we try to extend the idea to half integer quadrupole nuclears. In this first case is a chlorine, which is 35, which is spin 3/2. So we use exact T-HMQC sequence, and we see on the left we see 3 peaks. We identify the central transition and ST, which are both single quantum. The third peak puzzled us for a while because when we change the offset, it moves in a very strange way. And later we understand actually the 2-step phase cycle does not filter out the 3 quantum signal. So this is actually the 3 quantum coherence. And showing on the figure B that we show the efficiency as compared to the spin echo for the different coherence orders. And we can see for the double quantum, it's also very efficient. There's also interesting, there's notch in the middle. We are still investigating really what the cause of this notch now. But the most important is for the double quantum satellite transitions, the quadrupole broadening is 1/9 of the central transitions. This is a unique feature about spin 3/2. So by doing HMQC with double quantum transitions, we can obtain nearly isotropic spectra for the quadrupolar spin 3 quadrupolar nuclears with 1-step transfer by proton detections. And here shows the benefit of the line narrowing to resolve a 2 non-equivalent chlorine site in a pharmaceutical compound we call ISOX2. And in this case, the quadrupolar coupling broadening is much larger. So if you acquire with single quantum, it's a bigger blob. But if you do the double quantum correlations, you see 2 result peaks. But of course, the satellite transition is subject to first order quadrupolar interaction. So the magic angle must be very precisely set. Okay, so this is a side note for IF calibration. When you use this small rotor to calibrate the indirect IF, because normally signal is very weak, often quadrupolar nuclear, and often it's pain to pack this tiny little rotor without damaging the cap. And here just showing measuring the Bloch-Siegert shift to the protons, even though it's a very small shift, but we can measure very accurately by long spin echo. And we can obtain this kind of mutation spectrum from the Bloch-Siegert shift. We can back calculate the B1 field. And this comes handy for this small, fast spinning probes without the need of actually observing that nuclear, the signal from that nuclear. Okay, now I'm going to, let me see, why did not advance? Okay, oops. Now I'm going to switch the nuclear to MQMAS and STMAS. MQMAS is a widely experiment, again, first introduced by Lucio Friedman to refocus the second order quadrupolar broadening. STMAS, another variant, is slightly more efficient, but again, requires very precise magic angle settings. And both of them have a major issue, which is the efficiency tanks when the CQ gets bigger. So here the simulation, Simpson simulation done by Ivan, showing that how the efficiency varies with CQ as a ratio of mu Q over mu 1. And most case is in order of the mu of mu around 10. You can see here that the efficiency start to get drop and drop very rapidly if the CQ if the CQ gets bigger. And then showing in the middle, the black curve shows that if we use a long pulse STMAS, and because you use this long pulse and this level crossing mechanisms, that we can manipulate, obtain the ST satellite transitions with high efficiency, even if the CQ gets very big. So the key of this experiment is so-called the ST-selective pulse. When you apply RF to a satellite transitions, it mutate all the transitions. And for the central transitions, because it's narrow, it's always on resonance, then it will start to scramble and saturate and eventually going to decoherence the signals. So the trick is move that the RF far away from the central transitions. By doing so, we can drop that central transition RF element. Then the two satellite transition becomes two isolated spin systems. And we can achieve efficient manipulation by using long pulse. And here on the figure on the right showing the LP MQMAS efficiency as a function of the offset. You can clearly show that it increased with offset. And we typically use offset about a couple hundred kilohertz to have the best efficiency, but also within the tuning bandwidth of the bandwidth of the probe. So if we control the RF for rotor-period long pulse, we can control the RF to make the satellite transition selective pulse close to 90 degrees. Then we have STMAS. So just use a two long pulse, rotor-period long pulse with far off from the central transitions, and we increase the STMAS efficiency by more than order magnitude. For example, in this case, it's gallium oxide. It's a very sensitive model compound, but it has very large quadrupole coupling for spin 3/2. The smaller one is 8 megahertz, the large one 11 megahertz. And so far, no MQMAS and STMAS has been obtained for this compound, even though the sensitivity is very good. And so we get a whopping 50% efficiency. The spectra, one of the limitations of the STMAS is the T1 must be rotor synchronized. So the window must be equal to rotor period. In this case, this is only 14.5 kilohertz. So the spectrum is folded twice. And we apply this Q-shielding technique to unravel the field and obtain isotropic spectra with very sharp line width for the two gallium site. So now let's see how can we use a long pulse for MQMAS. And the key is, in this case, we make the RF a bit stronger to make the close to a pi pulse. Inversion of the satellite transition from 1/2 to 3/2, -1/2 to -3/2 will convert the central transition to the multiple quantum with 100% efficiency. But of course, the effective RF field is not homogeneous because it varies with the powder. So, but still, it's we can get much higher than just a few percent. So this is the pulse sequence we come up with compared to the regular Z filter sequence uses strong B1 field. We start with the green pulse, which is polarization transfer from the outer transition to the central transition. Then use selective 90 to excite to the central transition single quantum coherence. Then the two blue pulse, which is the key, which convert to the 3 quantum after the evolution, then convert back. Then use the Z filter for detection. And after we come up with the pulse sequence, actually it looks very close to the React sequence that Bob and Gang-Wu have developed many years ago. But in that case, the main difference is they use an on-resonance pulse and they use a fraction of use a pulse length, a fraction rotor period. In our case, we use rotor period long, but moving the pulse, the I frequency of the blue pulse far away from the central transitions. But the underlying mechanism, I think there's they come occurs with similar this level crossing mechanisms. And so here's the result for rubidium nitride, which is a model sample with a very small CQ. In this case, if you use a strong B1 field, we can get, for the regular MQMAS, we get a 28% efficiency, is 115 kilohertz IF. But for the long pulse, we get 36% with about using only about maximum of 12 kilohertz IF. So that makes the sequence particularly useful for low gamma quadrupole nucleus, because it's more difficult to get a strong gamma BE1 because of low gamma. And showing here is the MQMAS spectrum of the gallium oxide. Of course, the advantage of MQMAS is that it does not require very precise magic angle settings. So to conclude, I would like to conclude with the effective Hamiltonian for the IF, which is basically a scaling and the phase spread, and you don't need to worry about offset. The scaling is not a big issue because we use a long pulse, so the IF requirement is very low. For the phase spread, as long as you design pulse sequence with pairwise and with changes of coherence order, which is opposite to each other, then it's not an issue. And of course, best of all, we don't have offset. So I hope you'll find this long pulse useful for designing pulse sequence. And with that, I would like to thank you for listening, and I'll be happy to hear your comments and answer questions. Thank you.
All right. Thank you very much, Zhehong, for your very interesting talks. So, so as usual, I will perhaps like ask a question, a simple question, so that like the audience, you have some time to type your questions on the Q&A. So I'm just curious. So it's very nice that you show this like long process and how it improves like the STMAS and this efficiency. So I'm just curious, how would you expect the efficiency to change when you go to smaller rotor, when you can spin faster up to like 100 kilohertz? Would it be the same or would it be better?
Well, in terms of signal intensity, certainly, we get a reduction of the signals, which is, but fast spinning has a big advantage that because most of these experiments requires rotor synchronized T1 evolutions.
Mm-hmm.
So we can have a much broad, large spectral windows, and that can simplify the spectrum. Otherwise, with if the CQ gets very, very big,
mm-hmm.
the width of the powder pattern is several times over the width of the line width is several times of the spinning speed. There's lots of foldings, mm-hmm. and in that sense, going to fast spinning will be beneficial.
Is it very sensitive to the stability of the spinning frequency?
Actually, surprisingly, it's not. Actually, for the N14 HMQC, to our surprise, we don't see spinning sidebands along the N14 dimensions.
Okay. That
was a really big surprise to us. Which you expect for N14, they're spread 7 megahertz. If the 1D MS spectrum, you see tons of spinning sidebands. So should I open the Q&A?
Yeah, sure. So we have several questions. I will start by asking the first one asked by Frederick Porous. So how do the low power pulses compare in satellite transition inversion in the long pulse MQMAS to the more conventional approaches such as FAM, frequency sweep, hyperbolic secant, or boost pulses?
I think yes, I think in terms of the pulse sequence, for FAM actually is it's off the off the CT, but I think the main difference is this phase. I think most of the FAM and they apply in just a single pulse. They don't apply in a pairwise manner, and this is the key. If you don't do that, actually, you lose a lot of signals. I don't know if that answers Fred's question.
All right. Yeah, Fred, if you have more, you can keep commenting on the Q&A. But otherwise, I will go to the next question. Lucio said that it's a very nice talk, Zhehong. Are the long ST process you use cosine modulated to address all satellites?
No, actually, we use single. We do not use this DFS. We just moved off, jump the frequency to a couple hundred kilohertz off.
Okay, and then like the next question from Jay Lee. Does this new MQMAS with ST pi pulses require precise tuning of the magic angle, spinning stability?
The STMAS, yes. The MQMAS, no.
Okay. Okay, and the next question from Locus Rara Rao. How long we can what is the pulse length of the long pulses you were talking about?
Well, we typically use one Rotor-period to have to be effective, and you can use longer, but the consequence is the first T1 in evolutions. If we use one Rotor-period in a long pulse, we start the first T1 increment at one Rotor-period, and if you use longer, then you're missing more points at the beginning, and that can cause a phase distortion, and the first order phase correction problem to compensate the missing points in the T1 dimension. So in most cases, for the direct encoding with Rotor-period long pulse, but for the trapdoor case, it's the pulse is very, very long. It's typically in the order of milliseconds.
Okay, then it's not a question, but Jeffrey said that it's a great use of jottling frames. And then he just asked another question: why does double CP work so well for 14N compared to dipolar HMQC?
In terms of efficiencies are comparable, but again, I think in terms of the line width, the double CP is better because, as I said, that the proton T2 does not add to the line broadening on N14 dimension. But I also point out that you will see related peak because proton-proton spin diffusion during the spin lock period, which in the HMQC, the direct HMQC, you see a more quantitative correlations without the spin diffusion effect.
All right. So like if there are no more questions, I would like to thank Zhehong again for
I have a question for Zhehong.
All right, go ahead.
Why don't you take this and use it on our 017 N-acetyl VL sample that you guys still have down there? Is there a problem with spin 5/2 systems or?
Yes, actually, we already tried. I can probably someone already noticed that all the spectrum we have shown is for spin 3/2. The reason for that, we're talking about by moving the offset, to break into two isolated spin systems. That's only work for spin 3/2. For spin 5/2, we have 3 spin systems because we have 2 satellite transitions, and we both sweep and slew back and forth, and that can cause a little bit of complications. The experiment still works. The efficiency is not as good as spin 3/2, and we're in the process to see how we optimize and come up with that to improve the efficiency of the spin 5/2. Yes.
Well, that's a very important case.
Yes, indeed. Yeah. Indeed. Yeah, certainly. There are more interesting spin 5/2 nuclei than spin 3/2.
Yeah. Okay.
Bob, you want to introduce the next speaker?
Okay, so thank you very much, Zhehong, for a really nice presentation. All right, and our next talk is by Clemens Glaubitz from Frankfurt University in Germany, and we have a special guest to help Clemens in case he gets in